Okay, thank you. Can you hear me from the back? They don't complain. Okay, so thank you. Thank you to the organizers for giving me the opportunity to be in the last one. So I guess my role in part is to try to decide whether these forces that have been unleashed during this week here are evil or benign, okay? As you can see, I think they're benign. Okay, so the question is, I mean, you remember that in the first day, I was speaking about coherent structures, and I told you there was going to be a second day, which is today. Speaking about whether we could consider computers as scientists. I mean, basically, the theme of the whole talk is going to be how much science can be automated. And I chose that because science is the easy part. I mean, one thing is to try to understand what is the next movie that you want to see in Netflix, but science is a well-constrained system in which there are rules, so we can see whether we are playing by the rules or not, okay? So basically, also there is a question that you're in any kind of engineer, you know that if science can be automated, it will be automated by somebody. And then the question is, you have to decide whether that means that computers could substitute you, or me is probably too late, but you maybe, yes? Can you tell me? You can't hear me? Can you hear me now? Yeah. Better? Okay. Okay. So, I mean, this was one of the slides that I used on the first day. Is the scientific method, is the way that science is supposed to work. You know, first you observe something, then you explain it, try to explain it, then you test it, and blah, 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 blah. You keep going around that, okay? And then there is a bunch of smaller scale activities in there, which, you observe, you make observations, ask questions, gather information, blah, blah, blah. The question is how many of these things can be automated? And this is going to be the computer. This is going to be the woman that is going to try to substitute us, okay? And the question is which of these things can be automated and which ones are not, okay? I mean, some of them are obviously automatable or automatizable. I don't know how you say that. For example, make observations is what DNS has been doing for the last 40 years, okay? Gather information is also trivial. I mean, it's something that computers do that. They put it into a database, and then you have to do whatever you do with them. Make predictions is also a computer thing. Test predictions is also a computer thing. And then there are these things in blue, which are things that is not clear whether the computer can do for you or not. And this is what I'm going to try to apply to one example, and then see whether in that example the computer is doing any of these things, or these are things that are, at least at the moment, necessarily human. Okay. Now, why should we worry about this now? I mean, it's certainly not going to be happening tomorrow. Any of these things are not going to become computerized tomorrow, but maybe in 5 years, yes. So the moment is now to start thinking about them. And the first reason that we have to start thinking about that is because computers are getting faster, and you all know that. You know that every 25 years, the computers increase by a factor of roughly 1 million, okay? Which usually has meant that we do things which are more complicated every 10 years, okay? From my point of view, what I do is I simulate turbulence. In the 1970s, I was doing something like this, to the turbulence, okay? And then I started doing something like this, and then me or other people did things which are now fully developed three-dimensional turbulence, okay? And this is one way of using faster computers, okay? And when we do it that way, we know that there is somebody here, which is the one decided what to do and reading the analysis, which is us, is the thinker. They say the computers are not thinking, the computers are just computing things, okay? There is a limit for that. I mean, the largest thing that you can compute is roughly what can be computed in the largest computer in the world in 3 months. That's basically a PhD thesis. I mean, 3 months is not a PhD thesis, but 3 months of computer time for the largest computer in the world is a PhD thesis. It will take a few years, okay, because you have to You never get the whole machine. The machine, doesn't work. You have to write the software. You have to read it. So this is the limit of things that can be done. And on top of that is us trying to interpret things. Okay. But here there is another line, which is the line of 10 seconds. Okay. And the thing is, this line is 25 years away. 10 seconds is roughly 1 million times faster than 3 months. Okay. So when 25 years have passed, what used to take 3 months now takes 10 seconds. And that changes things a lot. Okay. For example, this thing that I could do in 3 months in 1970, 20 years ago, I could do it in 10 seconds. Then it was free. Okay? This thing that I could do in the 1990s, now it can be done also in 10 seconds. Then it's free, basically. Okay? And that means that thinking is beginning to change. Okay? The things that were being analyzed by us here now can be downloaded up to a point to the computer. Okay? Because you think of yourself, we try to think of ourselves as very intelligent things, but we are machines at the end. There is nothing not machine-like about us. We are just machines that do something, quite fast. And now computers are beginning to do them as fast as us. Okay, and that is changing things. Okay, the second thing that has been changing all this time is of course artificial intelligence. We have been speaking here about machine learning, artificial intelligence, and I told you the first day that can be classified into things. It's either symbolic or sub-symbolic. The symbolic is the classical kind of artificial intelligence in which there is a thinker, us, who makes hypotheses and then creates rules from the hypothesis, embeds those rules into an expert system and then runs it again. Something like what you were saying this morning. I like that. Okay, I like the physics part. Okay, but this is the old artificial intelligence. As I told you, people were doing this in the 1970s, and then the thing crashed for a while and then came back and blah blah blah. And now, of course, there is this new artificial intelligence, which is the sub-symbolic part. And the sub-symbolic part works differently. Okay, you don't start with a hypothesis. You start with a sample, with a lot of samples. Okay, you create algorithms. Okay, and this is done by something that is not an expert system. It's a neural network, a self-organizing map, whatever. Okay, the difference between this and that is that here we learn, and here the system learns. Okay, it's a basic difference. Here you don't really know what has happened. The system knows what has happened, but that's up to him or her or whatever. I don't know what the system is. Okay, and if we forget this part of the artificial intelligence, what happens is that we don't learn. Okay, and there are two possible outcomes to this. We can decide not to learn, to completely outsource our thinking to something else. Okay. Or we can try to learn what the system has learned, open the box, okay? And there is a huge branch, I can tell you, there's a huge branch. You look for this acronym in the web. This is called Explainable Artificial Intelligence. And there is a big community on that, because there are other reasons why people want to know how the computer works. I might want to know how the computer works, what the computer has done, because I don't want to be left behind. There is a lot of lawyers that want to know what the computer is doing in case something goes wrong, in case the plane explodes or something like that, whose fault it is, okay? It's because the computer didn't think correctly, because the programmer didn't think correctly, because there was a cosmic ray that just downed the plane or whatever. So this is something that is important. It's something that I think that we should always try to do that. Don't try to apply a neural network unless you have a way of opening it and looking inside. Okay. So, question. Let's now try to start looking at these questions now. Okay. Now that we know that the opportunities is that the computers are faster and they are thinking in a way that is basically different from us. Okay, what are these things can be automatized? Can we ask the computer to ask questions? Do they frame hypotheses? Can they judge those hypotheses. Okay. And I'll give you this example. I want to go through this example, which is something I've been playing with for the last year or so, last 2 years maybe. The thing is, I, the thinker, put a meta question. I mean, the meta question is not a specific question. I want to know about this, okay? And in this case, I want to know about 2D turbulence, okay? 2D turbulence, there are several reasons why you can choose that. First is easy. It's one of the things that can be computed for free, okay? And then I think I know, or the community tends to think that they know how it works. So if the computer gets conclusions, I can second guess the computer, okay? Say, okay, well, what you have done is right, or what you have done is wrong, or what you have done is new. That will be fantastic, of course, okay? So the idea is, what I want to know is I have a two-dimensional field. I run it for a while, and then the field has changed. I want to know why. I mean, and basically, I am a control-minded person. If I want this to be different, what do I have to do here? Do I have to touch that vortex there? What you're seeing here is vorticity. Do you want to touch that vortex there? Do you want to touch that vortex sheet in there? I mean, what do you want to do? I mean, what things here are important for what happens later? Okay, this is going to be my meta question. Okay, and then how do I do that? Well, there is several things that I can do for that. The first thing is I want to define what is important, what is a relevant feature, okay? And a relevant feature is something I'm going to define it like something like this. You break this initial field into pieces or into subsets or something. You do something to one subset, run the two systems for a while, see whether something has changed or not, okay? If it has changed, that piece was relevant. If nothing has changed, that piece was not relevant for this particular question, of course. Okay? And there are things, I mean, the first thing that you have to check is whether there are relevant and irrelevant things, where some things are more relevant, some pieces of the flow are more relevant, some pieces of the flow are less relevant. And then there is a lot of things that you have to, or that you can decide for that. What to do to that piece, how long to run, okay? And these are things that unless you know the answer, they have to be tested, okay? At the end of today, well, at the end of this first part of the talk, you're going to be seeing something which is a couple of million runs of this. But a couple of million runs of this took 10 days, okay? So it's not terrible. It's something that can be done, okay? And in those couple of million runs, you test many things. I mean, the idea is to test many things. And here I give you two examples, okay? In this case, I'm doing an experiment in which I take a piece of the flow, you break the flow into this grid in there, you take one piece of the grid, and then put the vorticity in this piece of the grid, put it equal to 0, okay? And then run it, okay? This is what happens when you don't do anything, and the flow goes from this to that, okay? This is what happens when you zero this part of the flow here. And then, as you can see, basically nothing has happened. This thing was not important. This thing was not relevant for this particular perturbation. Doing this particular perturbation on the flow didn't do anything interesting, because you see, I mean, this vortex here is that vortex there. That vortex there is still that vortex there. Essentially, very little has changed after a while. Okay. In this one here, this one turned out to be important. Okay. You zero the vorticity there, and then this vortex is not there, now has become round. I mean, this thing is also different. There is a big hole here that was not there. This thing was important, and it is important to notice something. I could not have guessed that this thing was important. It was important that this thing was not. It's something that has to be tested. I mean, it's not that I went there and killed that vortex. No, I zero the vorticity here in a place where basically there is no vorticity. I zero it there in a place which was whether originally there was not vorticity either, but this one turned to be sensitive, and this one turned to be insensitive. So these are things that you have to test. So you test them. I mean, you test them, and then also make sure that that something has happened. I mean, that there is a real difference between one case and the other, not in this big norm of the flow looks different, but in the details of what has happened to the perturbation that you have put in there. This is another case, but this is basically the same idea. The perturbation that I am putting here is not zero in the vorticity. It's just changing the sign of the vorticity within that little piece. Okay, and then this tends to be an irrelevant set. I mean, this little box in there tends to be not sensitive to what I'm doing. And you see what happens here initially. This is the difference between the perturbed and the unperturbed flow. Then you run it for a while, and you see that, okay, well, it moves a little and then decays. Okay, if you do this for one cell that turns out to be sensitive, then it's something completely different. You change it here, okay, and then the thing rearranges the whole flow. This is the difference between the two flows. So the fact that you have blues and yellows there means that it's not that you are destroying vortices that are moving. So the thing that was here now is there. Okay, so the whole flow has changed, and it has changed because this perturbation has turned out to be important. And looking at what you have done, looking a posteriori at what you have done, you can almost understand what has happened. You see here in both cases, I'm changing the vorticity, and the two cells have a lot of vorticity. Actually, they were chosen by me a posteriori just to do the slide, so that both of them, the initial magnitude of the perturbation was the same, but the final was very different. And then you see here the vorticity was strong, but it had different signs. Okay, so I changed it, and then nothing happened because those two signs are going to cancel each other. Okay, while here it was basically all of the same sign. So if I change it, then I'm changing something. Okay, so now you have to test these things. Okay, you have to let the computer search around. Okay, and how do you do that? Well, the way I'm doing here, you take the flow, change it into a subset, and you test whether these subsets are important or not. You do this for all subsets. You label these subsets. Okay, you say this thing was important, this thing was not, this thing was important, blah blah blah. Okay. You repeat it for many initial conditions. You typically run this. This is not the way. This is just for the slides. Typically, break that into a grid that is somewhat finer than this. Then you repeat this maybe 1,000 times or something like that. Do statistics, okay? And basically, the statistics that you do is you create a label training set. What I am doing is I am classifying the flow into cats and dogs. Okay, this is a cat, this is a dog, this is a cat, this is a dog. And now you launch one of these discriminators to discriminate between cats and dogs. Okay, what is that make a cat a cat? What is that makes a dog a dog? Okay, and this is the nest. This is how you do your set. I mean, there will be many of these subsets. Each of them with a relevance ranking. Okay, this is high, this is low, blah blah blah, and you have to test this for different times. Of course, you don't know over which time you have to test these things, and then for each of them you store some properties. Okay, because what you want to know later is which is the properties of a cat that makes a cat a cat, which is the property of a dog that makes a dog a dog. And in this case, for each of these subsets, I am storing the entropy within the cell, the rate of strain, the magnitude of the rate of strain, and then the kinetic energy within the box, and shows these three. Okay, so now on top of that, you launch a classifier. A classifier in this sense is something that for a particular property, for example, for the entropy, tries to decide whether there is a threshold for the entropy in which all the relevant things are to one side and all the irrelevant things are to the other side. And in 1D, you can do this by hand. Otherwise, you use something that is called a support vector machine, which is a classifier that you can get in MATLAB or in something like that. Okay, it's basically It's like a cluster, but it's not a K cluster. I think it's for classifying is much better than K clustering. It just looks at the, here, it just looks at the border. It doesn't care if there are many things here and many things there. It just looks at where to put this threshold in such a way that a minimum number of samples are misclassified. Okay, this is how it just adjusts the thing like that. Okay, and then you get here something which is classification efficiency, which is essentially how many samples are classified correctly. Okay, in this case here, which is for this particular initial perturbation and for this particular variable, 98% of the samples were classified correctly. In this case here, which corresponds to the thing here, roughly half of the things are misclassified, which means it's as good as chance. Okay, so this is a relevant diagnostic variable for this experiment. Okay, and this is an irrelevant diagnostic variable for this experiment. Okay, now what do we have up to now? Well, what are these? My understanding of this is that these are questions by the computer. Okay, the computer is not making a smart question, but it's making questions. I mean, it's asking questions. It's asking questions to the flow. What happens if I do this and then choose this variable? Well, then I get this answer. Okay, so these are the questions. These are the computer theories. Okay, now you have for these questions, and then you try to explain which of these things make sense or not. You say, well, this variable is important. Okay, the computer theory, the outcome of this is that the computer now has a theory of the flow. The things which are important for two-dimensional turbulence are vortices. Okay. Now, this is one possibility. There are others. I mean, there is no reason. You have to do more experiments. You have to choose more variables. It is not clear that for all the experiments that you do, the theory that you have is the same. And actually, they are not. I mean, there are two possible theories that my particular experiments have found. Okay, these are two experiments. In which case I was playing with the vorticity of the cell. In the other case, I was playing with the velocity of the cell. Okay, in the case in which I was playing with the vorticity, then, not surprisingly, the computer found that the relevant quantity was the total entropy in that cell. In the case in which I was playing with the velocity, not surprisingly, the kinetic energy was the important thing. Whenever the kinetic energy was high, that thing was sensitive to experiment with the vorticity, with the velocity. Whenever the entropy was high, this thing was sensitive to playing with the vorticity. That was not always true. I mean, there are cases in which you do something with the velocity and you end up with the result that the vorticity is important. And then you could sit down and say, okay, why? Okay, or you can let the computer do a little more for you. Okay, and do a little more for you is, okay, now I have my set, my training set. Okay, and I say, well, I know for this training set, I know which things are important, and I know which things are important because the vorticity is high, or because the energy is high, or something like that. But I mean, that's good for the computer. The computer goes there and tests for the vorticity. That's not good for me. I really want to know more about the structure. I want to be able to do physics with that. Okay, and the vorticity is an extensive quantity. It's an intensive quantity. I want to know what else do all the cells that have something that are important. What do they have in common? So you let the computer build a template for you. And a template is basically a conditional flow field around things which are important from the point of view of the vorticity, from the point of view of the velocity. For example, these are these two cells here that I know are important from the point of view of the kinetic energy. Okay, they're important for a particular experiment, which is the experiment in which I change the sign of the velocity in that cell. Okay, and then I say, okay, how do the flow look around that? Okay, And then you essentially build a conditional average. And this is something like a POD, but you cannot do a POD with this because of the invariances. Okay, this flow is invariant to rotation, is invariant to reflection. You can change the sign of the vorticity, and the flow will still work. So you have to, for each of these cells, you have to create a set of actually 8 cells in which this flow rotated by 90 degrees, 180 to 270, and the same thing flipped right to left. And then for each of these set of things, you choose the one that looks more like the first one, for example, and you add them and do an average. And you create something which is a dipole. A dipole for me was a surprise. I mean, I was not expecting dipoles. I was raised on the idea that two-dimensional turbulence is a gas of vortices, it's a set of vortices. That was the idea that everybody had in the 1980s, okay? And dipoles, of course, I mean, people knew that they were dipoles, but they were not considered important. Apparently, they're important, okay? You see there are two. I mean, in all the experiments that I have done, I have only ever found vortices or dipoles, okay? And a vortex looks like a vortex, and a dipole looks like a dipole. You see two vortices that have a jet, and this is where the kinetic energy is, okay? As I tell you, in the 90s, in the 80s and the 90s, there was a bunch of people doing 2D turbulence. That was the thing to do at the time, because it was possible to compute. 3D turbulence tended to be expensive, okay? And then the idea was, and this guy, Montgomery and McWilliams, I mean, they essentially got the idea that 2D turbulence could be explained like a bunch of vortices, okay? I mean, 2D turbulence is not a completely artificial flow. It's what happens in the ocean. It's what happens in stratified flows, or is close to what happens in stratified flows. Geophysical people like 2D turbulence because it really looks like something like that. What is important for a rotating flow, okay? And this is what you get. This is a vortex, and this is a vortex dipole. So this is okay. Now, what are the dipoles? Well, dipoles were known to happen. I mean, even if this guy 6 years before, I think that this is wrong. It was not Montgomery, it was McWilliams. But okay, a guy in there, okay? Notice that there were dipoles, said, okay, well, these dipoles form and then decay and nothing happens to it. Well, apparently, something happens to them, okay? They even had a name. They were called modons, okay? And they're supposed to be the thing that gets blocked in the North Atlantic and blocks the weather in Europe for a couple of months, okay? So now we have two theories.